Okay, now recall we had the unscaled graphs, and now we're going to scale the graphs. To scale, the first scaling we're going to do is we're going to define a cycle as what happens when you go completely around the circle. And we're going to label this axis now as our t-axis, the horizontal axis as our t-axis. And we're going to label t in cycles. Now, complete revolution around the circle gives us a complete cycle of the sine or of the cosine function, so that 1 is going to appear here. This is one cycle, or this point is at one cycle, the point where we get back to our starting value, where the sine reaches 0, where the cosine reaches its maximum value. So our first labeling of this axis will have t in cycles. Now, our vertical axis, and I've gone ahead and called this the y-axis, and I've called this the y-axis. This is perfectly compatible with the fact that we used the y values from this picture. Down here, what we now call the y values, the vertical axis values, are the x-axis values from this picture. And I didn't call this y, I was referring to this as much as I could as vertical axis. But now we'll call this the y-axis, even though down here these y values actually represent values of x here. In other words, what's y here is not the same as what's y over here. So we forget about the x and y that we used here. We've already got our graphs, and we're going to proceed accordingly. So if this circle has radius a, we make that assumption, then the values of y here go from negative a to a. And that's, of course, consistent with the fact that if we're here, we're a units above the center, because that is the radius of the circle. Here, we're a radius below the center, that would be at negative a units. And same here. Our graph will go from our maximum value a to our minimum value negative a, as will this one, maximum value a down to minimum value negative a. Now, we're calling this a sine curve. We're calling this a cosine curve. We haven't actually defined the sine function and the cosine function. Well, we're going to do that now. So I have this statement in orange. If a equals 1 and t is measured in the arc distance around the circle, that is, t is how far you've moved around the circle along this arc to get to these points. Okay? So a is 1 and t is in arc distance, and that's going to give us our sine function and our cosine function. Now, if a is 1, then I can relabel this. Instead of being a, this is 1. That's what that 1 is doing there. And we have a negative 1 down here for negative a. And I've got a 1 here and a negative 1 here. And now I've got, well, you see the projection line here. So here's 1, here's negative 1 vertical, 1 above the axis, negative 1 relative to the axis of 1 unit below. In this case, okay, the arc distance is going to be our coordinate, our t-coordinate. So what's the arc distance? Well, the arc distance completely around a circle of radius 1 is 2 pi, for the simple reason that pi is the ratio of diameter of circumference to diameter. The diameter is 2 times the radius, so the circumference has to be then 2 pi times the radius, diameter times pi. Okay, well, anyhow, you should be very familiar with that. The arc distance then for a complete cycle is 2 pi if the circle has radius 1, which is our assumption. So now I'm labeling the t-axis from 0 to 2 pi here and also here, so that one cycle corresponds to 2 pi. One cycle corresponds to 2 pi. And of course I can subdivide one cycle into a half cycle or into quarter cycles. And I've done that more clearly here. Here's a full cycle, here's half a cycle, here's a quarter cycle, and this is, of course, 3/4 of a cycle. Half of 2 pi is pi, half of that is pi over 2, and we have 3 pi over 2. So those are the coordinates if we're measuring an arc distance on a radius 1 circle. Now, it turns out that arc distance on a radius 1 circle is the same as radian measured. Okay? Now, I've made the comment here, if A equals 1, circumference is 2 pi, and that's equal to the arc distance around the entire circle. Down here, I do a little bit of explaining radian measure. I've got 3 concentric circles here and 2 rays, and there's an angle between those 2 rays. Okay, that angle could be measured in degrees. There's nothing wrong with that except that it gets really bad doing higher mathematics, at least at the calculus level, if you're trying to do it in degrees. You don't want to go there. You want to do this in radians. So we define theta as, well, if the radius of the circle is 1, theta is just the arc distance. If the radius is bigger than 1, then the arc distance is going to be bigger than the angle in radians, okay? And we correct for that if we divide the arc distance by the radius. So theta is arc distance divided by radius. Arc distance divided by radius is the same on all of these circles. So on a circle of radius 1, wherever radius 1 is, the radius is going to be 1 and the arc distance is going to be the angle. So this is completely consistent with the way I've described the scaling of this graph. Okay, this theta is going to be the same for all circles. It's going to be the same as it is for the radius 1 circle. And theta is actually unitless because distance and radius are going to be measured in the same units. So when we divide them, we get a unitless quantity, but we can still call that unitless quantity the radian. And we note that one cycle being the same as 2 pi radians, there are always 2 pi radians for a cycle because distance around the circle is always 2 pi times its radius. So when we divide the arc distance around the circle by its radius, we always get 2 pi. Okay, now, another application. We imagine that this circle represents the path of the tip of a windmill blade, and say a large windmill with a blade of radius 100 feet. And of course we got this on a tall tower, so it's safe to run along the ground. We interpret the motion you would have to undergo to stay directly under the tip of the windmill as you move to the left and to the right. Okay, so you want to stay directly under the tip of this windmill, and this windmill is going through one cycle every 20 seconds. Now let's just think about it. Okay, if one cycle takes 20 seconds, then how are we going to relabel our graph? Our graph is going to have to then be labeled to go from 0 to 20 seconds in one cycle. Now, the way I've subdivided this graph, there are just a little more than 20 divisions, but not everything is consistent here, as you should understand. But we're going to say that the quarter cycle occurs then at about 5 seconds, half cycle at 10 seconds, 3/4 cycle at 15, full cycle at 20 seconds. So now we have another labeling of our graph, where now t represents time. It didn't represent time here. Well, time, if we said t is the time for one cycle, and units of time for one cycle, then it could represent time. But right here, t is just representing the number of cycles. And when we measure this in terms of arc distance or radians of angle, we get another unit that doesn't represent time. Now we're representing time. Time is 20 seconds for a complete cycle. Same down here. Okay. Now, what we're representing on this graph then is the y-coordinate of the tip of that blade as we move around the circle. So the y-coordinate goes up 100 feet above the center, back to the center, down 100 feet below, and up. Again, we want to make this on a tower that's plenty tall so that people don't get swatted by the blade as it comes by. This graph then would represent the position of the tip of the blade, the vertical position of the tip of the blade relative to the center of the circle. This, remember now, the vertical axis here represents the x-coordinates of the position on the circle. This graph would then represent the horizontal coordinate of the position on the circle. And that horizontal coordinate would represent where you need to be if you want to run along directly beneath this windmill blade. We raised the question of how fast you would have to run at the maximum. Obviously, when you're here, the windmill blade is moving directly up, so you don't have to be moving there for an instant. And then when you start moving, you can start moving pretty slowly, but by the time you get over here, the tip of that blade is moving this way, and you better be moving quite a bit faster than you were when you were standing still. Okay, we can make one quick calculation that between here and here, you've got to run 100 feet in 5 seconds. Well, 100 feet in 5 seconds is 20 feet per second, and that would actually represent the average slope of the graph between here and here. This is the magnitude of the average slope of the graph. So if we cut a chord across the graph here, the slope of that chord is going to be actually negative 20 feet per second. A rise of negative 20 feet, a run of 5 seconds, gives you a slope of negative 20 feet per second. And how fast you have to be going is just the 20 feet per second. Doesn't matter whether you're going this way or this way, you still got to be running 20 feet per second. Okay? Now that's your average speed. 20 feet per second is pretty fast. I think I might be able to still run that fast, but I'd be risking injury, so I'm not even going to try. Most people of college age can easily enough run at that speed, although it gets difficult if you start going much faster than that. Okay, well, how fast do you have to be running at this point? This is just a hand sketch graph, but we can draw a tangent line to the graph at this point, which is where the tangent line is going to be steepest, and it's going to have a slope of the greatest magnitude. And we can calculate the slope of that tangent line. Well, it looks like this point projects down to about here, so there's about 3 seconds, and there's about 100 feet here, negative 100 feet, so you got about negative 33 feet per second. Tangent line here actually comes out, closer to 40 or 50 feet per second, but over here they come out pretty close to 30 feet per second. So that this graph allows us to estimate our maximum speed along this path. Now, 30 feet per second is pretty fast. Most people can't run that fast. Fastest people can run is just a little over 40, maybe close to 41, but not 42 feet per second. So you got to really be pretty well hustling if the estimate is 30 feet per second. If it's 35 feet per second, you got to be hustling quite a bit faster. And there aren't many people that can run that fast. Okay. Now, I couldn't help it. I had to do the calculus analysis here, so I'm just going to briefly explain that. Now, if a equals 1, our function is y equals sine of t. But in general, if the amplitude is a, our function is y equals a times the sine of t, or a times the cosine of t. So if a is 100 feet, then this graph would be a times the cosine of t. Now, haven't gone into the details. The actual function that would represent this when t is in seconds would be 100 feet times the cosine of pi over 10 times t. And the pi over 10 times t comes out because you have to complete a complete cycle of 2 pi radians in 20 seconds, which means you have to be moving pi over 10 radians every second. So in relabeling, we haven't gotten to that, but that's what you need. In any case, the derivative of this is pi over 10 times the negative cosine of pi over 10 t times your 100 feet, giving you negative 10 pi times the sine of pi over 10 t. Maximum value sine of pi over 10 t is 1, and that gives us a maximum velocity of negative 10 pi feet per second, which is magnitude is 31.4 feet per second.